Hello everyone. In the last class we started discussing about the eddy viscosity model, and we looked at the zero equation models like the Prandtl Mixing model, Van Rist-Mixing model, Sebeeke-Smith model, okay. And then we started talking about the two equation models, and we derived the equation for the kinetic energy, turbulence kinetic energy, okay, from the first principle, and we found different terms in that, the temporal term, advection term, production term, diffusion term, right. And then we saw that we do not have any way to basically derive the equation for the basically the dissipation, right, or dissipation rate. So, what we did, we followed the basically different terms. I mean, most of the equations that we see, whether it is a mass conservation, momentum conservation, energy conservation, you have these terms available, the temporal term, advection term, and then you have the production term and the diffusion term. So, we use those terms and derive the equation, the dynamical equation, the transport equation for the epsilon, which is the dissipation rate, right. So, I have basically written those equations here. Okay, you can see this is my temporal term, advection term, dissipation term, and this is the source plus sink. Okay, this is the source plus sink. This is again I am giving you for the standard K epsilon, and as I told that K epsilon model is a class of model. I have been telling that the equation for the epsilon may differ depending on which model you are using. If you are using a standard K epsilon or RNG or basically realizable, right. And you can see there are several coefficients here, okay, which is sigma k, sigma epsilon, and then sigma C epsilon 1, C epsilon 2. So, the values of these also may vary depending on the model. Even for the same model, depending on when it was proposed, you have basically we have seen that these values evolve, and how these values evolve, basically you get the more and more accurate experimental data or the DNS data. You use these models and plot it and see when basically it matches perfectly with the your experimental data or the DNS data, those values you use. Okay. In fact, if you are using these models in a solver, you can change these values to suit your requirement, the values of basically C epsilon 1 and C epsilon 2. Okay. So, now we have two things, K, which is turbulence kinetic energy, unit is meter square per second square, right, and then you have epsilon, which is use unit is meter square per second cube. Okay. We are looking for nu T, right, which is eddy viscosity, whose unit is meter square per second. Again, we will go back to the dimensional argument. We want to use this K and epsilon and get this nu T, right. So, how do you do that? You can use this basically by going by the dimensional argument. So, this will, if you take K square by epsilon, right. So, this will become meter. So, this will become m to the 4 by second to the 4 by meter square by second cube, right. So, that will become meter square per second, right. So, your nu T must be proportional to, okay, your nu T must be proportional to K square by epsilon. Okay. We will also look at like how it is related to the argument that we have been making about the velocity scale and the length scale, right. But for now you can see by the dimensional argument nu T proportional to K square by epsilon, and then we use a proportionality constant which is called C mu. So, this will become C mu K square by epsilon, and if you use the definition of the eddy viscosity which is mu T, and it will be, this is the kinematic eddy viscosity, this is the eddy viscosity, this will become C mu rho K square by epsilon, right, this is epsilon. Okay. So, once you know the K and epsilon, which will you can get by solving these dynamical equations along with your mean flow equations, you can find the eddy viscosity, use this eddy viscosity in the equation that you have, the momentum equation as well as your energy equation, and you can solve the problem for the mean flow, right. For more advantage of this eddy viscosity model compared to let us say Reynolds model is that it provides more stability to your numerical system. Why? Because as we have been talking that if a problem has got higher numerical viscosity, it is likely to be more stable. Okay, in fact, it is more stable, right? Remember the argument that you had made about this Lax-Friedrich scheme, and we said that it is highly dissipative, right? Because it has got a high numerical viscosity. So, in effect, if you talk about the eddy viscosity, we are multiplying. So, we earlier, let us say you had mu del u bar by del y. Okay, but now by using the argument of eddy viscosity, your effective viscosity became mu plus mu t, okay, del u bar by del y, right. So, your effective viscosity increased. So, that means numerically it has become more and more stable, right. So, that is another argument in favor of the eddy viscosity model compared to trying to get a dynamical equation for the Reynolds stress itself. Okay. Yeah, so this is again I have put all the equations together, okay, for the K and for the epsilon, and I have basically indicated different terms. Okay. So, this is the production of kinetic energy and dissipation, and based on the model we have this the production of the dissipation rate, if I can call that, and this is the dissipation. Okay. So, these are all model terms. Okay. So, we saw that our mu t is given by C mu rho k square by epsilon, but how does it fit to our definition that my viscosity should involve a length scale and a velocity scale, right. So, you can compare, let us say if I compare it, so your nu t is equal to C mu k square by epsilon, right, but your nu t is also equal to basically k to the power half, which is a velocity scale multiplied by some length scale, okay, which I am writing as Lm. So, if you compare these two, okay, you can write the length scale as C mu k to the power 3 half by epsilon. Okay. So, this is your length scale. Based on this length scale, okay, you can remember this C mu is just a constant, okay, it is a proportionality constant. So, if you have know this length scale, you can define a number which is called the turbulent Reynolds number. Okay. So, you have seen the Reynolds number, now we are talking about turbulent Reynolds number. Okay. You might be seeing the different Reynolds, different turbulence model like low RE turbulence model, high RE turbulence model. So, that RE there basically indicates the turbulent Reynolds number. Okay. What is RE, turbulent Reynolds number? So, like the way you have the definition of Reynolds number, right. How the Reynolds number is defined? Let me write it here. Okay. So, this is Reynolds number is inertial forces by viscous forces, right. So, this is basically rho u square initial forces, this is mu u by L, right, that becomes the rho u L by mu, right. This is your Reynolds number. In the same spirit, we will define the turbulent Reynolds number, which we call as the turbulent forces, okay, basically the forces due to the turbulence stress, okay, and divided by the viscous forces. So, the region where the turbulent force is more dominant, that will be your high turbulent Reynolds number, where the viscous force is dominant, that will be your low turbulent Reynolds number, and as you might guess that where is the viscous force is dominant, very close to the wall, right, in the viscous sublayer, right. So, if you can elaborate it, okay. So, we will be writing it, so this will be rho u square, okay, this u square. So, we have to see what is the u square definition and divided by mu u by L, right. So, for the turbulent forces, the u square definition will be turbulence kinetic energy, because u is k to the power half. So, u square will be rho k mu, and this will be k to the power half. Okay, let me just see. Okay, so the k is k to the power half is our u. Okay, so let me just work this out u, and then yeah, okay. So, length, if you look at the length scale, this is k to the power 3 by 2 by epsilon. So, let me write that, okay. This is k to the power half divided by k to the power 3 by 2 by epsilon, right. So, if you work this out, this will become rho k square by mu epsilon, which is given here. Okay. So, remember this indicates the ratio of the turbulent forces, which is like given by this k square, and by the viscous forces, which is dominated by the viscosity multiplied by your dissipation, right. So, we will come back to this turbulent Reynolds number later when we talk about the low Reynolds number model. Okay. Now, the question is how do we determine the coefficients, right? Like say you have the, what are the coefficients you have? Mainly you have C mu, okay, which is basically the multiplying constant when you try to get this mu t from K and epsilon, okay, and then you have C epsilon 1, okay, and C epsilon 2, okay. We also had like nu alpha, okay, earlier, or I think there was another nu in the dissipation equation, right. So, let us try to get this C mu. Okay, again these are all empirical models, but still there is I mean a lot of experimental insights into deriving these values. Otherwise, these values can be anywhere, and you will not have a way to basically find out the value of this. So, if you talk about how do we get the determination of C mu, okay, what we are going to do? We are going to talk about something called local equilibrium. Okay, most of the models that you see, the Eddy viscosity models which are popular, they actually follow the local equilibrium. What it says is that your production is equal to dissipation, okay, locally. Okay. Now, if you talk about the production, okay, so the production is given by minus u prime e prime bar, okay, del u by del y, right, and we can equate it to basically your dissipation. But again this is stress, this is a stress, and if you go by the argument of the constant stress layer, this is equal to your u tau square, right, and in the log layer you have this u tau by k y kappa y, right. So, epsilon is nothing but u tau q by kappa y. That is one definition of your dissipation rate by going the local equilibrium. This is a very important assumption, and actually it fails in many regions, and that is why you get that your model is not behaving correctly. So, we are assuming your dissipation rate is equal to the production, okay, production of the kinetic energy, right. Now, if you go look at the turbulent boundary layer, okay, so you can also write it as the turbulent viscosity is equal to tau by del u by del y, right, and tau is nothing but your rho to rho u tau square by the definition of the friction velocity u tau, okay, and also you have del u by del y is equal to u tau by k y, which is the log layer, okay. So, if you combine these two, okay, this definition tau turbulent and del u by del y, okay, so you will get this value of rho u. So, this is basically rho u tau square, which is your tau turbulent by u tau by kappa y, right, that is your mu t, okay. So, and you can write as mu t by rho is equal to u tau by, okay, into kappa y, right. So, this is basically kappa u. So, your nu t is equal to u tau kappa y, right. So, remember this nu t, what is your nu t and what is your dissipation rate, and you can combine that, okay. So, let me write it here, nu t equal to u tau kappa y, and earlier we had epsilon equal to u tau by kappa y, epsilon equal to u tau by kappa y, right, and you can use this definition of kappa y here, epsilon is u tau q by kappa y, I believe, yeah, u tau q by kappa y, okay. So, you can combine these two, so that will become nu t u tau into u tau q by epsilon, this will become u tau 4 by epsilon, right. So, this is your nu t by going by the argument of the log layer and the constant stress layer, okay, but also the nu t is C mu k epsilon. So, if you compare these two, okay, you will get C mu equal to u tau square by k square, right, and u tau is nothing but your turbulent stress, okay, square. So, minus u prime v prime square by kappa square, right. So, this is your the value that we are getting by comparing in the turbulent boundary layer, right. So, we have seen in the experiment that the ratio, I mean typically the ratio of the basically the shear stress by the turbulent kinetic energy, turbulent shear stress by turbulent kinetic energy is around 0.3, where this is seen in most of the turbulent flows. So, then epsilon will be basically minus u prime v prime bar by k square, which will become 0.09, okay, c mu. So, this is how you get the value of c mu, okay. And this is typically, I mean very robust and does not change too much. On the other hand, you can also use the epsilon equation, and by comparing with the experimental data, okay, without going to the derivation, you get the value of this c epsilon 1 and c epsilon 2, which is around 1.44 and basically 1.92, and then these are the values which are used again from the modeling, sigma k equal to 1 and sigma epsilon equal to 1.3. Okay, these values have evolved over time. Okay, you can look at different models, and this value will be very different in different models. Similarly, your epsilon transport equation is also heavily modeled. It varies among different models. Okay, so K epsilon is a class of models. Okay, the last thing I want to discuss is the low RE formulation. So, like if you recall the Prandtl model and the von Ristring model, what we said that the model which basically works in the fully turbulent region away from the wall may not work very close to the wall, and the reason for that is basically the viscous layer dampens the eddies. Okay, so you have to make some argument that how the effect of turbulent forces go down very close to the wall, right, because we have this viscous sublayer very close to the wall. Okay, let us say here, where your value of the turbulent forces are not that dominant, right, the turbulent forces are not that dominant, right. So, like the von Rist changed the Prandtl model by adding some damping. The same thing is done in the low RE formulation of the K epsilon model, so that the K epsilon model works not only away from the wall, but also very close to the wall, right. So, what they have done, basically they have used different damping for different coefficients. So, this is f1, f2 and f mu, which is for c epsilon 1, c epsilon 2 and c epsilon c mu. So, these terms basically multiply wherever the c epsilon 1 you multiply with the f1, c epsilon 2 multiply by f2, and where the c mu, the definition of basically mu t, you multiply by f mu. Okay, you can see that these are the numbers which are functions of RET. Okay, and if you go very close to the wall, the value of RET decreases because the turbulent forces decrease, and that has been accounted by using these kind of functions here. Okay, in f2 and f mu, they also tried using the damping for f1, but they found that it basically does not affect the model that much. So, they have kept the f1 equal to 1, but they have used the damping based on the turbulent Reynolds number in f2 and f mu, and that gave us the formulation of the low RE formulation, so that it can work all the way to the wall, and you get the essential damping due to the viscosity incorporated in the K epsilon model. Okay, so, this is how you see. So, this is basically if you just look at the f mu, okay, which multiplies with your c mu, right. So, your nu t is basically f mu, c mu and k square by epsilon, right. That is what we had here earlier. I am observing the c earlier. So, you can see that very close to the wall f mu is much less than 1. Okay. So, that means your eddy viscosity is very small, but it will smoothly if you go away from the wall. Okay, it is going to increase, and if you go to the fully turbulent region, it becomes 1. Okay, and that your definition reverts to mu t equal to c mu k square by epsilon, right. Okay, one more topic that I want to briefly mention is the wall function. Okay, so earlier, like when the computers were not very powerful, okay, what you could do, like you know that how the flow very close to the wall. You know, there is a region where u plus equal to y plus, okay, and there is a region, this is typically y plus less than 5, okay, and y plus greater than 30, we have u plus equal to 1 by kappa ln y plus, okay, and plus C1 or B, okay, the intercept. Okay, this is the log law and this is the law in the viscous sublayer, right. So, what they used to do that you can actually provide, you can assume a velocity profile here, okay, very close to the wall. Okay, this is the node very close to the wall, and if you can assume or you give that profile to the model and ask it that you do not have to solve it, but you can use this profile directly. Of course, this is valid only when the boundary layer is in equilibrium and when the it is the fully turbulent velocity wave profile, right. If there is a separation or there is a reattachment, these things will not work because they will not follow this law. Okay, let us say there is a separation. Okay, your velocity profile will become like this in the case of separation, right. But for other attached flows, you can use these wall functions. Then the advantage here is that you do not have to resolve all the way to the wall. Okay, if you want to let us say resolve this y plus equal to u plus, you need at least 5 grid points, right. So, that will be minimum points to be y plus equal to 1 and then 2, 3, 4, 5. So, that you can resolve this region, the linear law. Okay. Similarly, here also we have to resolve in between you will have buffer zone, that also you need to resolve. Okay. So, you could use instead a wall function, okay, so that you can just model this entire thing using a assumed velocity profile for a turbulent boundary layer and just solve it. Okay. So, of course, it will give you a poor prediction for separation and reattachment. Okay. And the other thing is that you should not put grid points between 5 and 30. Okay. Why? Because this is the region of the buffer zone where none of these laws are defined. Okay. So, generally you are asked to basically put the y plus less than 1 or around 1. Okay. If you are solving to the wall, if you are using wall function, then put it the value above 30. So, that you put the wall function up to 30 which are following this law, and after that your model is resolving through the simulation. Okay. So, these are the wall functions. Okay. So, these finally, we have the limitations of the K-epsilon turbulence model. It is valid only for the fully turbulent flows. It will give poor predictions as we expect for the rotating flows and swirling flows. Okay. Despite of the fact that we have incorporated the low RE model, it is not very good for flows with separation, okay, or even with shocks, or if there is a lot of swirl or rotation, the assumption of the local equilibrium or the boundary equilibrium breaks down, and this does not give you the good prediction. Okay. So, this is usually preferred for high RE applications, okay, where there is no separation or reattachment. If you want to let us say solve, so we use this model for a complicated turbine blade where there is a lot of separation. Okay, for example, the flow is coming like this and this is separating. This model is likely to not give you the good prediction. K-epsilon model is not good if you have like separation and all like in turbomachinery flows. Okay. And similarly, flow with strong shocks, this is not good. So, what we will see in the next class is that we will look a model which works very well very close to the wall, and that model is called the K omega model. But then there are issues with this model also. So, we will try to blend the K epsilon and K omega model, and that will give you a model called SST K omega model. Okay. So, this is what we are going to discuss in the next class, and that will be our final class on this Raynes modeling. So, I hope it gave you a good picture of how these models work, what are the eddy viscosity model and how things work, and after that we will look at these models. I mean it will give you an idea that how to use this model, how does this coefficient work. Okay. So, with that we will stop the class today, we will meet in the next class. Thank you.